Now we work out a problem, and the rotor of a turbine 13.6 kg in mass. So this is the turbine rotor. That means all the blades, rotating parts are modeled as a disc, and the mass of the disc is 13.6 kg, and that is supported at midspan of a shaft with bearings 0.4064 meter apart. So this distance is between the center of the bearings is 0.4064 meter. That means 40.64 cm or 406.4 millimeter. So just have a feel of the distance between these two bearings. And the rotor is known to have, okay, so let me first write L equal to 0.4064 meter, and unbalance is mass into eccentricity, (7.9 kg meter), and the rotor is known to have an unbalance of this. Determines the forces exerted on the bearings at a speed of 6000 rpm. So the operating speed is 6000 rpm, and the diameter of the shaft is 2.54 centimeter. 54 centimeter. That means T is equal to 0.0254 meter. So now what is the natural frequency? Natural frequency we know is omega n, and that is the critical speed of the rotor. So what is the critical speed of the rotor? Root over K by M. So what is K? K is, we are assuming so they have told you to assume that assume the shaft to be simply supported at the bearings. Generally, if the bearings are self-aligning, that means if the bearings do not prevent the slope of the shaft, we assume them to be simply supported. So self-aligning bearing means they allow slope of the shaft, only they prevent displacement in this direction, but they allow slope. So that's why these self-aligning bearings are assumed as simply supported supports, simple supports rather. They are assumed to be simple supports. So for simple support, you know K is 48 EI by L cube, and which is 48 for steel shaft. E is 2 into 10 to the power 11, and I is for a circular shaft 5 by 64, 0.0254 meter, 4 by 0.4064 cube. The diameter of the shaft is 2.54 centimeter. That means 1 inch. So this comes out to be 2.74 into 10 to the power 6 Newton. So the critical speed is 2.7674 into 10 to the power 6 divided by 13.6, and this is 449 radian per second. And the operating speed is 6000 rpm, that means twice pi n by 60 radian per second. So 6000 into twice pi by 60, so this is 200 pi radian per second, that means 628 radian per second. So this is actually, this we call capital omega. So from this n, that is we call the capital omega. So capital omega is 628 radian per second, and capital omega is greater than the critical speed. That means the turbine is operating supercritically. Now we know that Z by E is equal to, if you neglect damping, here there is no mention of damping, so we'll neglect damping. So this is omega by omega n square by omega by omega n square minus. So here you just look at the formula here. So when omega is greater than omega n, so we, and this damping part is 0. Since omega by omega n is greater than 1, so to make it positive, we write it as omega by omega n square divided by omega by omega n square minus 1. Actually, to avoid the negative sign here, because if omega by omega n is greater than 1 and you keep it like this, then the denominator becomes negative. So this Z by E becomes negative. This becomes negative because the phase is actually 180 degree. That means Z and E are in opposite directions. So here Z is in this direction and E is in the opposite direction. Z is in this direction and E is in the opposite direction. That's why the negative sign is coming. But to avoid the negative sign, we just write the formula like this. So, and you are given ME. So ME is 0.02879 kg meter. M is the mass of the rotor. So mass of the disc rather, mass of the disc kg. So from here you find out E, and you find out the value of E, and E is 0.0000211 meter. So now Z by E is this. So Z by E is 628 by 449 square divided by 628 by 449 square minus 1. So from here you get Z as 4.326 into 10 to the power minus 4 meter. So this is the value of Z you get. Now the question is how to get the bearing forces. So what you do is, suppose this is your shaft within simply supported bearings, and you give a force at the mid span. Let that force be P. Now you find out what is that force which creates a displacement of this capital Z. So that you can do by the simple calculations. You can get from this simple calculations. So 48 EI by L cube into Z, or K into Z, and K you have already computed, that is 2.74 into 10 to the power 6 into 4.326 into 10 to the power minus 4, and if you calculate you get this as 1185.32 Newton. Now what are the forces transmitted to the bearings? Half of this force P. That means if this is P, the bearing forces are P by 2 and P by 2. So the bearing force on bearing is equal to 592.66. Now you can also draw the bending moment like this. This is the bending moment diagram, and you know this is PL by 4. So P by 2 multiplied by P by 2 multiplied by L by 2, so PL by 4, and from here you can find out sigma as Pm into D by 2 by I, because Y is half of diameter of the shaft. Now the next question is, you reduce the diameter. You reduce the diameter from here to here, and now you find out what are the bearing forces. So you reduce the diameter, so now D equal to 1.905 centimeter, 1.905 centimeter to 0.01905 meter. So K is 48 into 2 to 10 to the power 11 into pi by 64 into 0.01905 to the power 4 divided by shaft length cube, and this turns out to be 9.24 into 10 to the power 5 Newton per meter. So in this case omega m is root over K by m, that means 9.24 into 10 to the power 5 divided by 13.6, which gives 260 radian per second. So now omega by omega n is 600 by 260. So previously it was 600 by 449, and now it is 600 by 260. Now it has become supercritical, it has gone to the region which is more supercritical than the previous one. So omega by omega n is higher, so it has gone more in the supercritical region. So if that is so, then from here you get Z by E. So now the shaft is more supercritical. So more supercritical. So omega by omega n square, omega by omega n square minus 1. Shaft is now the whole system, the shaft disk system or the rotating system is more supercritical than the previous case. So from here you get Z equal to 2.55 into 10 to the power minus 4. So the deformation has reduced. Here the deformation was 4.326 into 10 to the power minus 4. Now the deformation is this. So now if you calculate the bearing forces, you get it as 231 . So since the shaft disk system has become more supercritical, the forces in the bearings have reduced. That means you reduce the diameter from 2.54 to 1.905 and the bearing forces have reduced. That means you are now have more safety than before, which is actually contrary to our common sense, because we think that if we increase the diameter it becomes safer. But what happens here? We decrease the diameter and the bearing forces are less and it becomes safer. So if the bearing forces are less, then sigma is also less, because sigma is my by I and m is PL by 4. So here the shaft disk system is safer. So you have made it more supercritical and you have reduced the bearing forces. So thank you.